Hello, my name is Adnan. I will be talking today about the chemical processes and economics of carbon sequestration. Carbon sequestration is the process involved in carbon capture and the long-term storage of atmospheric carbon dioxide or other forms of carbon to mitigate or defer global warming. It has been proposed as a way to slow the atmospheric and marine accumulation of greenhouse gases, which are released by burning fossil fuels. Carbon dioxide is naturally captured from the atmosphere through biological, chemical, and physical processes. Artificial processes have been devised to produce similar effects, including large-scale artificial capture and sequestration of industrially produced CO2 using subsurface saline aquifers, reservoirs, ocean water, aging oil fields, or other carbon sinks. There are three options for processes: terrestrial, physical, and chemical. Terrestrial sequestration involves the capture and storage of carbon dioxide by plants and the storage of carbon in soil. During photosynthesis, carbon from atmospheric carbon dioxide is transformed into components necessary for plants to live and grow. As part of this process, the carbon present in the atmosphere as carbon dioxide becomes part of the plant. Geological sequestration refers to the storage of CO2 underground in depleted oil and gas reservoirs, saline formations, or deep and mineable coal beds. Once CO2 is captured from a gas or coal-fired power plant, it would be compressed to approximately 100 bar, so that it would be a supercritical fluid in the fluid form. The CO2 would be easy to transport via pipeline to the place of storage. The CO2 would then be injected deep underground, typically around 1 kilometer, where it would be stable for hundreds to millions of years. Chemical sequestration is capturing CO2 at the source, also known as the combustion exhaust, and sequester the carbon in commercial products that are long-lived, stable compounds, for example magnesium carbonate or CO2 clethrate. Biological sequestration. It's the storage of atmospheric carbon in vegetation, soils, woody products, and even in aquatic environments such as the ocean. This process is most commonly known as photosynthesis, but is a form of carbon sequestration. Increasing the amount of plants and vegetation, especially trees, can help remove larger amounts of CO2 from the atmosphere. Oceanic sequestration is an additional, less explored process that involves collecting carbon from the ocean. Chemical sequestration can happen in three types, mainly electrocatalysis. It's reducing carbon dioxide by a copper complex to an oxalic acid. Mineral carbonation is another way, where we would be storing carbon dioxide in carbonate mineral form. This can happen by allowing CO2 to react with metal oxides, example magnesium oxide and calcium oxide. As you can see here, the reactions calcium oxide and magnesium oxide both react with carbon dioxide to form CaCO3 and MgCO3. Chemical scrubbers is a widely used method in power plants. It's primarily used in capturing CO2 from coal and gas-fired power plants. There are two types to that: wet scrubbers and dry scrubbers. In wet scrubbers, the process exhaust gas can also contain water-soluble toxic and/or corrosive gases like hydrochloric acid, HCl, or ammonia, NH3. These can be removed very well by a wet scrubber. Dry scrubbers systems are used to remove acid gases such as SO2 and HCl primarily from combustion sources.
I'm Elizabeth Basista, and I'm going to talk about the second type of carbon sequestration, which is physical sequestration. It's also known as geological sequestration, which is the process of storing carbon dioxide in underground geological formations, such as old oil and natural gas wells. That involves three main processes, which is capturing the carbon dioxide, transporting it, and then injecting it into the well. There's two types of storage, which is permanent storage and semi-permanent storage, where the carbon will be taken back out eventually. So the first step is carbon capture, and carbon must be collected after the fuels are combusted and the CO2 emissions are produced. So this collection process must occur at the location where the energy is being generated. The capture technologies usually involve a chemical or physical means to sequester the CO2 emissions, like we talked about before. Which technology is used depends on the concentration of carbon dioxide, the temperature of the emissions, and the corrosiveness of the emissions, so how much sulfur or nitrogen is present in the flue gas. The collection of the emissions does add to the cost of producing the energy. The burning of the fossil fuels, the power plant production costs will be higher, but in the end, the capturing process is necessary, and it is the first step of the carbon sequestration process. Then you have to transport the carbon dioxide that you captured at the plant, and this is usually done by pressurizing the CO2 so it is in liquid form, so it can be transported by tanker truck or by pipeline. The carbon is then injected into the old well in its pressurized liquid form into the porous rock, where it will either stay or it will be used for something called enhanced oil recovery, which is when the carbon dioxide is injected into old non-producing oil wells to reduce the viscosity of the remaining oil and allow it to flow and be collected more easily later on. Again, this is called enhanced oil recovery or tertiary recovery. Not all oil wells use this technology, but the ones that do see increased production, and it also stores carbon, so it's a dual purpose. Physical sequestration only occurs so far in the coastal plainer region of the United States and a little bit in Alaska and the Rocky Mountain. It takes a certain geological formation to be able to do this technology, and the USGS released the first assessment in 2013 about the average estimated storage potential in the US. They estimated that about 2,400 to 3,700 metric gigatons of carbon dioxide would be able to be stored in the US in existing wells. This is actually almost sufficient to store all of the carbon dioxide that is in our atmosphere already, which is about 3,200 gigatons. This assessment is for only the technically accessible well potential, so it's only the wells that we can inject using today's engineering practices and techniques. So that does mean there is opportunity for increased storage potential. So back to how we capture this CO2, it can be captured from carbon dioxide emissions from power plants, which they scrub the flue gas, and the core of this scrubbing system is an absorber containing a scrubbing solution that absorbs the carbon dioxide from the power plant's flue gas at low temperatures. So you can see from the schematic that the flue gas will first reach a wet scrubber where it is cooled and freed from the sulfur dioxide particles, which can prove to be corrosive to the pipes and the transportation devices used. A fan then transports the flue gas into the absorber, and the absorber uses scrubbing solution at the head to remove the CO2 from the flue gas. This scrubbing solution usually is composed of a solution of amines. Then the low CO2 gas is scrubbed with water before it exits the absorber in order to remove any remaining residue of the scrubbing agent. The low CO2 concentration flue gas is then released back into the atmosphere.
My name is Gorgone, and I'll be introducing environmental impacts of carbon sequestration. In the United States, we're responsible for about 1.6 gigatons of carbon emission from burning fossil fuels every year. We're able to use carbon sequestering to deplete about 0.5 gigatons of this per year. This leaves us with a net 1.1 gigatons. This has led to a significant increase in atmospheric CO2, going from 280 parts per million to 380 parts per million in the last 250 years. This has caused problems such as increase in sea level, increased wildfires, floods, and droughts, changes in the amount and timing and distribution of rain, and finally the disturbance of coastal marine ecosystems and organisms. Oceanic impacts of the environment are the ocean's primary long-term sink for CO2 emissions caused by humans for a global net uptake of about 2 gigatons of carbon per year. The seawater in the ocean and atmospheric CO2 react to make a more acidic ocean, which hurts marine organisms and ecosystems. These organisms depend on the formation of carbonate skeletons, which dissolve in the acidic water. Studies show that the dissolution of these skeletons are catching up to the formation of them, which could cause the extinction of these organisms and other problems. The fact that we know so little about the ocean acidification and deliberate ocean fertilization may mean that the problem is worse than it seems. This could also lead to the problem worsening. Terrestrial and biological sequestration normally is accomplished naturally through forest and soil. However, we use conservation of these things to ramp up the amount of CO2 removed. We do this by restoring and establishing new forests, wetlands, and grasslands. We can also reduce the emissions of CO2, such as cutting down on agricultural tillage and stopping wildfires, even though the United States is required to do this to meet land management objectives. A majority of the carbon that is sequestered due to forests naturally regrowing from when we knocked them down over 200 years ago. However, the current terrestrial storage for CO2 is vulnerable to problems such as forest fires and disease, causing permafrost to thaw and severe warming of the forests. This is very prevalent in the United States. A potential terrestrial sequestration idea would be to restore the United States forests and soils to their original historic levels before logging and cultivation took place. However, this is very unrealistic and would displace a large percent of agriculture and disrupt many other activities presently enjoyed by the people of the U.S. An estimate of the amount of carbon accumulated would be 32 gigatons due to forests and 7 gigatons due to soil. The reason why carbon sequestering is not as prevalent as it needs to be is because there are significant trade-offs associated with it. And although converting farmland into forest and wetlands would help the amount of CO2, help wildlife and water quality, it would also increase flood storage, the amount of food that would be lost is not seen as economically or universally helpful trade-off. So the geological sequestering is man-made and is the way that humans try to help reduce the amount of CO2 in our atmosphere. And we do this by capturing the exhaust from fossil fuels in a pipe and inject it 1 to 4 kilometers below the ground level in porous rock. But this only accounts for a very small amount of carbon sequestered per year. However, we are looking to improve this. Geological sequestration permanence depends on the trapping mechanism and how well it worked. When CO2 is injected into the ground, it will rise until it reaches an impermeable barrier. In theory, this should trap the gas for thousands to even millions of years. However, this is not 100% perfect by any means. Some of the CO2 will eventually move and dissolve in the ground. It also can dissolve in groundwater, and some may be trapped in the form of carbonite reacting with the rock around it. Also, CO2 can slip through and never reach a barrier and just go right up back in the atmosphere. The amount of carbon that can be stored underground is dependent on the storage site. According to the U.S. Department of Energy, the total amount of carbon that could be stored in physical traps, coupled with depleted oil and gas reservoirs near fossil fuel plants, is estimated to be about 38 gigatons. The total amount of storage capacity of deep porous rock that contain saline groundwater is about 900 to 3,400 gigatons of carbon. This is much more widely distributed, and we know less about the effectiveness of this trapping method. However, another idea that has been proposed is unminable coal beds, but again, there's not enough knowledge for this to be done in a beneficial way. What needs to be done is by 2050, the U.S. emissions of CO2 are projected to double if we stay at the pace that we are currently at. And a study in 2007 stated that sequestering over the next 2 to 3 decades, which would now be 1 to 2 decades, will significantly help long-term to stabilize levels of CO2 in the atmosphere and help global warming as a whole. However, substantial action is and was required to do this. The U.S. Climate Change Society program created computer models showing what would be required to have a significant impact. And if we reduce 75% of global emissions, which is a significant and pretty unrealistic amount, we would have to be reduced to stabilize the atmospheric CO2 at around 550 parts per million, which is about twice the amount of CO2 in pre-industrial atmosphere and still 45% higher than it was in 2007.
Hello, my name is Bobby Stafford. The economics of carbon sequestration. Costs of human-engineered carbon capture include the following: the cost of the equipment, in addition to the cost of the absorbent chemicals used to remove CO2 from emissions. The cost for absorbent chemicals is a variable cost because it varies with the level of production. As more electricity is produced, more emissions are generated, and thus more absorbent chemicals must be purchased. The cost for equipment is a fixed cost and is independent on the level of production. Carbon sequestration also includes opportunity costs, such as the cost for energy uses in the form of electricity generation. Carbon capturing reduces electric power output and increases fuel input, resulting in an energy penalty. Once the carbon is captured, it must be transported to and stored at a long-term storage site. The fixed cost of carbon storage includes the cost of pressurized transportation vehicles and the cost of installing the pipeline. Variable costs of storage include labor payments. The current government programs and travel incentives include the following: Big Sky Carbon Sequestration, DOE Voluntary Reporting of Greenhouse Gases Program, Regional Greenhouse Gas Initiative, the Plains CO2 Reduction Partnership, California Climate Action Registry, and the Climate Registry. Research funded by the U.S. National Science Foundation concluded that fuel costs can increase up to 136% using carbon sequestration technology. Fuel costs, which determine the marginal cost and ultimately the profits for a power plant, would double with implemented carbon sequestration. In addition to increased operating costs, carbon capturing systems require a large capital cost. Considering the required steam for carbon capturing that can't be used towards the total power generation results in a loss of revenue and a profit penalty. Without an implemented carbon tax, carbon sequestration remains economically unsustainable. The President of the United States has recently signed legislation that gives a tax credit to companies that can capture or reuse their CO2 emissions. This implemented tax credit would give $50 per ton of CO2 that is buried, in addition to $35 a ton for CO2 that is reused without a limit on the amount. Combining this tax credit with the existing research in carbon storage and capturing could allow carbon sequestration to compete with low-emission forms of generation by the year 2030. In conclusion, carbon sequestration is beneficial for the environment but may not be economically feasible. Capturing the carbon dioxide emissions adds cost to producing the energy. Sequestration of CO2 occurs both naturally and artificially. Carbon is naturally absorbed by the ocean, trees, and soil. However, the industry can take steps to help mitigate the amount of carbon dioxide emitted by fossil fuel production and energy conversion.